Unit 5, Part 3. This is, again, Exercise 1B from page 92. I was explaining the theoretical import of the base columns. Right, so we have an argument form, a particular argument form, first premise, second premise, conclusion, spoken formally, given any conditional, and also given the negation of the antecedent, am I entitled to infer the negation of the consequent? A triple dot for conclusion there. That's the question, right? That's the that argument form has an infinite number of substitution instances, right? Because P and Q are sentential variables. They take as substitution instances any sentence, right? There are an infinite number of sentences. Just plug in different P's and Q's, different sentences, different particular sentences, over and over and over again. You get a different instance of this form, right? So here's the issue. How could I possibly know of this infinite number of substitution instances of this form that none of them are such that the premises come out true and the conclusion false, right? That's my task. And we're only able to solve that task when we understand that when we've built up our system of logic as truth functional, and we understand what it means for the sentential connectives to be truth functional, right? There's that infinite number of substitution instances, but since the only thing that goes into determining whether each sentence form that makes up the argument is a set of sentence form, the only thing that goes into determining whether each sentence form is true or false is the truth values of the component sentences, right? That's what it is to have a truth functional system of logic, to have each statement form truth functional, made or built with truth functional sentential operators, right? So that fact of truth functionality, the fact that the only thing that goes into determining the truth value of each statement form is the truth value of the components, brings the infinity down to a finite set, right? For this example here, where there are two sentential variables, this finite set, right? Each row here itself represents an infinite number of substitution instances, as I was saying in part 2, right? But they are all equivalent, each one in this set, right? Each substitution instance for this argument form where both the P and the Q are true, or both the antecedent and the consequent of the conditional that is the first premise, when they're both true, they're all equivalent with regard to the question that concerns us, right? Which is, what are the truth values of the premises and conclusion? What are the truth values of the statements that make up the argument, right? Because what do we need to do? We need to see whether there are any arguments where the premises are true and the conclusion false. So we're concerned with the truth values of the premises and conclusion. But the only thing that goes into determining the truth values of the premises and conclusion is the truth value of the components, right? So this lists everything, the truth value for the P and the Q, exhaustively lists all the factors that determine the truth value of the statement forms making up the argument, okay? So that's why, right, that sort of truth, the fact of the truth functionality of the sentential operators making up the statement forms, that makes possible the truth table test for an argument's validity, right? All we do is compute the truth values. Was it unit 3 we did computing truth values? Compute the truth values here, when P is Q and Q is true, is this true or false, right? So truth values will go here, 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 under the major operator, here, 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 TF, TF, whatever it is, and here. And for all these, so we compute the truth values of the premises and conclusion, and then we just inspect the truth table. If we have a row where all the premises come out true and the conclusion false, right? If some row appears where it goes true, true, false, right? Then we point to that row and we say, this is a counterexample, right? This substitution instance is a counterexample. Again, substitution instances, there are sort of two senses of it. There's, when we now that we're talking in truth table terms, we will use the term substitution instance to speak of a particular row in a truth table, but the point I've been stressing this part and the last part is that each such substitution instance is itself representative of an infinite number of actual substitution instances, where substitution instance there means particular argument with particular meaningful English sentences. Okay, but we point to whatever it is, where it's true, true, false. We say that substitution instance is a counterexample, and since this counterexample exists, this argument is in fact invalid, right? And now the big, huge climax is when we inspect if we inspect a truth table for a valid argument form, which we will do, I'll do 1D in a moment. This one will turn out to be invalid, and there will be a counterexample. But if we look at the whole truth table, and nowhere in this truth table does there appear a row whereby all the premises come out true, in this case both premises come out true and the conclusion comes out false, if there's no row which matches the definition of a counterexample, all premises true and conclusion false, then now for the first time we can say, no counterexamples exist, right? Of the infinite number of substitution instances of this argument form, I can say confidently that none of them are such that the premises come out true and the conclusion false, right? That's what you can say. Why? Because it doesn't come out here, having exhaustively listed all the truth values of the component sentences of the sentential variables, exhaustively list all of them, right? That's the only thing that matters to going into determining the truth value of the statement forms that make up the argument. And having completed the truth value, you don't have any substitution instances with the true premises and false conclusion, so there aren't any substitutions. So that's it. It's important you get some sense of how the truth functionality of our system, the truth functionality of all our sentential operators, brings infinity into our grasp and reduces the infinite number of substitution instances to a manageable, testable, finite set. Okay, so now that's grasping the theory is sort of the hard part, and it's important you know what you're doing when you're doing it. The actual computation of truth values is pretty easy, right? It's just, this is a very easy one. We'll do more complicated ones where the formulas are more complex. But in each case, it's just a reiterated application of the truth tables for the basic formulas, right? So here it's just P hook Q, it's exactly the same as the actual truth table given that defined this thing in this operator in Unit 2. So what is it? Remember, the conditional is only false when the antecedent is true and the consequent is false. Right? It's false there, but it's true here, here, and here. Notice I'm doing it column by column, as Klenk recommends you do. Page 81, I think. 81, third paragraph. Go column by column. It's easy to compute that way. You'll see more patterns. Right, so it's true, false, true, true, right? That is, when P is true and Q is true, P hook Q is true, the conditional is true. Conditional is always true when the antecedent is false, so true here, true here. It's only false when antecedent is false in the conclusion, and the consequent is false. Right? Not P, it's just the opposite of P. So true, so I'm just looking at P, true, true, false, false becomes false, false, true, true. Not Q, it's just the opposite of Q. True, false becomes false, true, false, true. So now I'm just looking for a row to match my definition of a counterexample, right? You sort of become like Terminator, right? You're trying to match a particular, trying to get a match for a particular row that looks like this, right? All premises true and conclusion false. Right? This should be your image. We're talking a lot in Unit 6 about the image that goes with each concept. But this should be your image for a counterexample. T's under the major operator for all of the premises, conclusion false. So terminator, boop, 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 boop. Do I have one that matches? That's true. What do we got here? These are ambiguous. Make sure your letters are not ambiguous. But true, false, false, not a counterexample, because it's not the case that all the premises are true, right? Here, the second premise is false, so not a counterexample. So this does not prove that the argument is invalid. So far, at least, the argument is valid. Here, both premises are false, so it's not a true, true, false. Doesn't match this, right? So far, I don't know that it's not valid. Here we go. True, true, false, right? Here, the premises come out true and the conclusion false. So when you're answering, this is what you do. You point to it like this, put an arrow here so that I know that you have seen that this is the row. You write CE, right? And you write, this is a counterexample. This proves the argument form is invalid.